I'd like to now explain what the curse of dimensionality is, or what is typically meant in the literature by it. We've mentioned it before, and we'll study it again, and we'll have our own definition of the curse of dimensionality. But let me explain to you what is usually meant by this. People say this, so remember the last section. If G is sufficiently smooth, then the error of the 2D composite trapezoidal rule looks like this. True integral of a two-dimensional function, g of x and y, dx dy, minus the composite trapezoidal rule, sum I running from 1 to n, sum j running from 1 to n, 1/2. And then there's an average plus gxi minus 1 yj plus gxi yj minus 1 gxi minus 1 yj minus 1. Yeah, so average over the four corners of a rectangle. And then we saw last time that this is bounded by h squared over 12, and something that depends on the function. So it's the maximum over x and y of the second x derivative plus the maximum over x and y of the second y derivative plus another term, h4th divided by 144, 12 squared, over the maximum of the fourth derivative, g of x and y. Okay, well, so what's the dominating error term? That's of course the h squared term. If h is really small, then the h over 4 goes to 0 much faster. So this is the dominating error term. So this is how the rule behaves like. So the composite trapezoidal rule in 2D has an error that behaves like this, order h squared, which is order of n to the minus 2. If I express this in the number of points that I'm using. And the important observation is that this is the same as in 1D. So in the 1D composite trapezoidal rule, the error behaves like h squared. And if you recall how we derived this, we essentially took the one-dimensional error and we integrated over it again. And we only got additional errors. So that error that we already have didn't get smaller. If I now were to derive the composite trapezoidal rule in multiple dimensions, nothing would change. So it would still be order h squared. So the same holds true for multi-D. So, and then what is usually done, we express the error in terms of the total number of points, because that's a fair comparison between all of the different methods. So the overall number of grid points in D dimensions that's the total number of points, capital N, that's little n to the power D. Yeah, so n squared in 2D, n cubed in 3D, and so on. And so the little n is actually a big N to the dth root, so capital N to the 1 over D. Well, and now we can express the error in the total number of points. Is this one, so it's O over h squared, which is O over O of n to the minus 2, and n to the minus 2, well, little n we have seen here, so that's O of n to the minus 2 divided by d. And well, I've shown this to you for the composite trapezoidal rule. There's no reason why this should be different for any other quadrature rule. It has a certain 1D error, and then to make it a 2D quadrature rule, I integrate over this error, and this error stays the same. So this also holds in general. If the quadrature rule in 1D behaves like this one, n to the minus alpha. Yeah, so the order of convergence is alpha. Then in multi-D, we get a behavior measured in the total number of points, which is on the order of n to the minus alpha divided by d. And now if I look at this, and again, so this is called the curse of dimensionality in the literature. If I just look at this, I see that the convergence rate behaves badly with the dimension d. Yeah? So say I use the composite trapezoidal rule and I use it in 10 dimensions. That only has a convergence order of 2 over 10, 1 over 5, which is really, really, really slow, much, much slower than Monte Carlo. And don't even imagine doing these methods in 100 dimensions. So let me formulate this observation. So the convergence rate thus deteriorates with increasing dimension d. And this is called curse of dimensionality in the literature, usually. All right, so that's the curse of dimensionality. It has appeared before, and it will appear again.